All right, so there are these voids that are in between the superclusters that are, they were actually discovered in the 1980s, and we found voids around in other areas of anyhow, there are these voids out there where there's no galaxy, no stars, um, and in fact, one of the things about the Big Bang Theory is we should be able to, using the scientific method, we should account for the fact that there are these voids. There's regions where there's lots of galaxies, and there's regions where there are voids. And of course, the Big Bang Theory has, with it the fact that all space, all time, all matter, and energy were formed 13.8 roughly billion years ago, and during the Big Bang, all the hydrogen and helium were created, and all the atoms, all the light atoms of hydrogen and helium, and then eventually the stars started to form and create heavier elements, and of course the stars form galaxies, and in between the galaxies there are these voids. Now we actually have a way of seeing way back into the universe, not with visible light, but with microwaves. So if you look out into the universe, there is this there's certain wavelength, which is called the cosmic background radiation, and it's the same everywhere in the universe. When we map this cosmic background radiation with satellites, it's harder to do it from Earth to get a really good picture of this, but we get this background radiation, and we see kind of hot spots and a little bit cooler spots in the background radiation, and the cooler spots are where the voids are going to be in the overall universe. All right, so this is the overall structure of the universe. All these voids and clusters, well, superclusters really. And all right, so that is our chapter. I want to turn now to. Let me move this over so you guys can see it really well. Move it over here like that. There we go. All right, I want to do a couple of examples here, or at least one example of the Schwarzschild radius. All right, so here's the equation. The Schwarzschild radius is equal to, this comes from the escape velocity, setting the escape velocity equal to the speed of light. So c is the speed of light, g is the universal gravitational constant. Isaac Newton knew, well, it was measured after Newton's death, but he certainly knew about it. He just didn't know what the value for it was. It's 6.67 times 10 to the minus 11th. The mass in this equation has to be in kilograms, and then of course the speed of light is what it always is, 3 times 10 to the 8th meters per second. Don't forget, you got to square that. All right, so let's do an example. So I'm going to do an example about the radius of. Let's go with something that is exactly 3 times the mass of the sun, right? So it's going to be so start with 2, right? So I'm starting right here. 2 times 6.67 times 10, so e to the minus 11th times. All right, so 3 times the mass of the sun would be 3, and the mass of the sun turns out to be 2 times 10 to the 30th kilograms. All right, so 3 times that. And remember, this is a 2. I was saying 3 when I wrote it. All right, so 2, and then you take the speed of light, 3 times 10 to the 8th. All right, that's in e. And you got to square that. All right, so let's see what this comes out to be. And this would be pretty much the smallest black hole that could happen, even though, you could take any mass and put any mass in here, but not just any mass will become a black hole, of course. All right, so let's get our calculator. So it's 2 times 6.67 times 10. Let's see, the exp to the minus 11th. All right, so times 10 to the minus 11th, and then times 3 times 2 times 10 to the 30th. Of course, that's 3 times the mass of the sun, and then you divide the whole thing by 3 times 10 to the 8th. 3 times 10 to the 8th. But of course, we have to square that, all right, and that equals. And so this would be so if we were to round this to one place past the decimal, so this is literally in meters, right? So this would be 8,893.3. So the answer is here. Let's write that down. So 8,893.3 meters, right? So the answer is in meters. All right, so I just wanted to do that example. Let's see, let me try another example as well. Oh, I wanted to introduce the inverse square law. All right, so this is a relatively easy problem. Remember, the only variable is the mass. All right, so here, let's do another example here. All right, so with the one that I'm about to do, this is what the inverse square law is. It says the flux is equal to the luminosity. Remember, we talked about the luminosity earlier, divided by the area that the luminosity takes up, which is 4 pi divided by the distance squared. That's squared, not a z. It looks kind of like a z, so that should be squared. All right, so if I rearrange this equation and solve for d, really that's what you're generally looking for. It's going to be the square root, all right, of the luminosity divided by 4 pi. Right? All I did is I brought the d over here and then brought the f over here. All right, and then take the square root. Right? We're not interested in the negative root because the negative root is, it's meaningless to us. All right. So, for example, let's say, all right. So suppose the flux were 3.2 times 10 to the minus 9th, and the luminosity of our sun, of course, is 3.9 times 10 to the 26th. That's a very well-known value. If we plug in the flux of the flux that I just gave you, 3.2 times 10 to the minus 9th, we should be able to get what the distance is. All right, so I put all the numbers in right there. So let's get our calculator out and we'll try that. All right, so there's the flux. Here, let me rewrite that. So it's 3.2 times 10 to the minus 9th. All right, so that's what goes right here in the denominator. All right, so what we have to do is we take 3.9 times 10 to the 26th. All right, so we have let's clear that. So 3.9. This is the luminosity of our sun times 10 to the 26th. All right, so that's that's in the numerator right there, divided by 4 pi, 4 times pi, and then times this flux, this 3.2 times 10 to the minus 9th. All right, so we do that, and we get, so that's going to be what's inside of the square root, and then we take the square root of that, and that'll give us the distance, and so that's the distance in meters. All right, so the distance in meters turns out to be, well, so it's approximately 9.84. 9.84 or 85. So it depends on how I round this. If you were to count the zeros, there would be 15. There would be 15 places past the decimal. So it would be 9.84. Well, I'll call it 9.85. So 9.85 times 10 to the 10 to the 15th. Or actually, I think it's 10 to the 16th. Sorry, times 10 to the 16th. Here, let's check on that. Let me look at the answer again. Sorry. All right. So there's the decimal point right there. So that's 369. So that's 12, and there's 15. Yeah. So that's 16. So 9.85 times 10 to the 16th. And then we divide that. Okay, so let me move that over just a little bit. If we divide that by what 1 light year is, so we divide it by 9.46 times 10 to the 15th, this will give us approximately how many light years away this is. All right, so it's about 10.4. All right, so this turns out to be, so this is the number of meters, which turns out to be about 10.4 light years away. So a star like our sun would produce, give us a flux of roughly 3.2 times 10 to the minus ninth, which is something we can definitely, pick up in our telescopes without any difficulty at all. All right, let's see. Let me see if I can pause this. All right, so let's try to do this problem. Here, we'll start over. So suppose we had a star that was 5 times the luminosity of the sun. So there it is. That's in the numerator. So 5. Here, let's put this in there. So 5 times 3.9 times 10 to the 26th. All right. So and then we divide by. All right. So then divided by in parentheses 4 times pi. 4 times pi times, all right, and let's say our flux was 2.2 times 10 to the minus 13th. All right, so you'd be given all these numbers. So 2.2 times 10 to the minus 13th. So exp to the minus 13th. All right. So how far away would that star be? So you do this, and then now what I just did, we didn't take the square root yet. So we're going to do the answer, and then we take the square root of the answer. For this calculator, it's this button right here. It'll take the square root of what's right here, and so that'll give us an answer in meters. All right. So that's the number of meters. I wish it would do it in scientific notation. Anyhow, so here we'll just count this from where the decimal is. So 1, 2, 3, 1, 2, 3. So that's 6, 9, 12, 15, and what did I say? 15, and then 18. So this would be like 2 points. So here, I'm going to round it to 2 places past the decimal. So it would be 2.66. Right, because it's 2. So 2.66 times 10 to the. So it should be 2.66 times 10 to the 19th. That should be 19. Sorry, 10 to the 19th. All right, so sorry about that. And here, let me pause this. So in meters, it would be 2.66 times 10 to the 19th. Or if you divide by this number, that'll give us the number of light years. All right, so divided by 9.46 times 10 to the 15th. All right, so how many light years away is this thing? So it turns out to be 2,807.4. So that's what I would write. 2807. So 2807.4 light years away. And that's a decimal point. Sorry. Make sure that looks like a decimal point. All right. So, it's more than 2,000 light years away. Well, that would be, under these conditions, that would be the distance. So this is a way that we measure distances in